Today we will study about unit 1.3, that is solar cell. So first of all, what is a solar cell? A solar cell is a semiconductor device which directly converts sunlight into electricity by photovoltaic effect. Photo, that is the word used for light, voltage, that is for the electricity or the voltage of the electricity. So it is directly in one stage, single stage, it is converting light energy into electric energy. So it is a semiconductor device because it is made up of semiconductors. So the image here shown in the image, figure 1.3.1. So it is silicon solar cell. Silicon, the most commonly used semiconductor. Okay, so the name photovoltaic, that is commonly used with the solar cell. Photovoltaic cell. Okay, light to electricity, converting semiconductor device. Solar cell, that is a basic block of solar photovoltaic technology. It means the system, the first component in the energy conversion system or the electricity producing system, that is the solar cell. It is a device that directly converts sunlight into electricity without any other intermediate conversion step. So input, that is light energy, that is from the sun. So the solar radiation output, that is in the form of electricity. So the factors which affect or govern electricity generated by the solar cell are, the first one is intensity of light. Intensity means higher intensity of sunlight, the more electricity will be generated. Area of the cell, so it is also directly related with electricity production. So larger area, the more electricity will be generated. The angle at which light falls on it. Okay, so the power generated by a solar cell is optimum when sunlight falling on it is perpendicular to its front side. Means it should be, angle should be 90 degree, straight above. The sun should be straight above the solar cell. Okay, some other factors like conversion efficiency, amount of light, operating temperature, they also affect the electricity generation, and we will, in our coming units, we will discuss each of these factors. Now some of the parameters of solar cell. First parameter is short circuit current. So what is short circuit current? It is a maximum current that can be produced by a solar cell without affecting its construction. Higher value of the short circuit current, so we consider it as a positive measure. Higher value means better cell. So unit ampere or milliampere. So the value of this maximum current that depends on the cell technology, cell area, amount of solar radiation falling on the cell, angle of the cell. So all of the all of the factors which we have seen above, they all affect the short circuit current. Open circuit voltage. So open circuit means load is not connected, it is open. The terminals, the output terminals of the solar cell, they are not connected, they are open. So no load is connected. In that time, the voltage between these terminals, that is the open circuit voltage. So higher value that is desired from a solar cell, it is measured in volt or in millivolt. Next is maximum power. So maximum power. Power basically what? Power is basically the product of current and voltage, because here we are generating DC. So we will be dealing only with current and voltage. Phase and this power factor, these things we won't be dealing here. The higher value of PM, maximum power, the better is the cell. So it is measured in watt. A solar cell that can operate at many current and voltage combination. Means it may not be fixed voltage and current, the combination. There could be different combination. but it will produce maximum power only when operating at certain current and voltage. That voltage, that current, that is Im and Vm. We denote it by Im and Vm, the current at maximum power and voltage at maximum power. There is a curve, the current and voltage curve of a solar cell. And here is the curve, voltage on the x-axis, current on the y-axis. So solar IV curve. Next is current at maximum power point, or Im. So this is the current which solar cell will produce when operating at maximum power point. Maximum power point, that is the point on the curve where we are getting the maximum power. So the specific voltage and specific current, so that voltage, that is voltage at maximum power point Vm, current at maximum power point Im. Just we can examine it in the graph. Here in the graph, in the curve, both of the terms they are given. Okay, voltage on the x-axis, current on the y-axis. So the dark point, that is indicating the maximum voltage at maximum power, and this dark point on the curve in between the curve, that corresponds to the maximum power point. Correspondingly, the voltage here on the x-axis and current on the y-axis, they are Im and Vm. So there is a rectangle formed where within the curve one more rectangle is formed on taking short circuit current and open circuit voltage. So a larger triangle, the dotted line, larger rectangle, larger rectangle and lower rectangle. Two rectangles are there, and the ratio of these two is known as fill factor. So what is fill factor? It is the ratio of area covered by Im Vm rectangle, means the inner one, first inner one, to the area covered by Isc Voc, means open circuit voltage, short circuit current rectangle. That was the outer rectangle. What does that gives? That the numerator Vm into Im, that is less, so the value is less than 1, fill factor. Efficiency, next thing. Efficiency is the maximum output power divided by the input power, the ratio of the output and the input. So it is given in the terms of percentage. So what is the input here? Input is in the form of solar radiation. Output is in the form of electrical power. So the ratio of both of these power, that is the efficiency. Now coming to solar cell technologies. Solar cell technology, the name of the technology is the name of the material which is used for manufacturing the solar cell. The material used in solar cell, different type of materials are having different properties. So correspondingly, the material which is used for manufacturing the type of solar cell is having a different value of the parameters. The same parameters which we have just studied: efficiency, short circuit current, fill factor, open circuit voltage, all of these parameters. So in the table, first solar photovoltaic technology. First technology is crystalline silicon solar cell. Correspondingly, it is of two types: monocrystalline silicon. Second one is polycrystalline. Polycrystalline silicon is also known as multicrystalline silicon. And the material used, that is monocrystalline silicon in case of first type of monocrystalline silicon cell, and multicrystalline silicon in multicrystalline or polycrystalline solar cell. Efficiency 14 to 16%. In this case, next technology, that is thin film solar cell. So the solar cell type is amorphous silicon, cadmium telluride, copper, indium, gallium selenide. 3 types. Correspondingly, the same materials. Amorphous silicon is used for amorphous silicon solar cell. Then cadmium and tellurium are used for the next type solar cell. And the next one, copper, indium, gallium and selenium. Efficiency, amorphous silicon is having very less, 6 to 9%. Cadmium, tellurium, 8 to 11. Copper, indium, gallium, selenium, that is having 8 to 11% efficiency. It means that in the monocrystalline silicon solar cell, efficiency is higher. Next type is multi-junction solar cell. So it is having consisting of gallium, arsenic, indium, phosphorus, germanium, and efficiency is 30 to 35%. Now different parameters which are for different type of solar cells. The first one, monocrystalline solar cell, efficiency we have discussed. Then cell area 5 to 156 centimeter square. Open circuit voltage 0.55 to 0.68. Output current for the short circuit current 30 to 38 milliampere per centimeter square. Fill factor 70 to 78%. It is percent. Multicrystalline or polycrystalline. These two, monocrystalline and polycrystalline, they are the most commonly used solar cells. Mostly in the market, commercially available cells, they are either monocrystalline or polycrystalline. Then similar parameters are available for multicrystalline. Just a very minor difference is there. Output current, output voltage, that is from 0.5 to 0.65, current 30 to 35 milliampere, and fill factor 70 to 76%. Next, amorphous silicon, efficiency 6 to 9%, cell area 5 to 200 centimeter square. Then open circuit voltage 0.7 to 1.1 volt, and current 8 to 0. No, not 0. It is 15 milliampere per centimeter square. Fill factor 60 to 70%. Cadmium telluride, efficiency 8 to 11%. Cell area similar to that of amorphous. Output voltage 0.8 to 1. Current 15 to 25 milliampere per centimeter square, and fill factor similar, 60 to 70%. Copper, indium, gallium selenide, efficiency 8 to 11%. Cell area 5 to 200. Output voltage 0.5 to 0.7. Output current 20 to 30 milliampere per centimeter square, and fill factor 60 to 70%. Last one, gallium indium phosphide or gallium arsenide or the germanium. So it is having a combination of these elements. Efficiency is much higher, 30 to 35%. Cell area 1 to 4 centimeter square. Then output voltage 1 to 2.5 volt. Output current 15 to 35 milliampere per centimeter square, and fill factor is 70 to 85%. Here, the 3 common type of solar cells. First one is monocrystalline cell. So what is the difference between this monocrystalline and polycrystalline? So monocrystalline cell contain pure silicon. So it is cylindrical in shape. Okay, now to minimize the cost, now to optimize the performance, 4 sides of the cylinder are cut out to make silicon wafers. In silicon wafers they are made. It provides the monocrystalline solar panels their appearance. The appearance that look like this cylindrical, and the wafers they are cut and they are cylindrical. So these cells can easily be recognized from their uniform look and even colored external surface because of high purity silicon. I mean, they are pure. Monocrystalline cells, they are pure, and correspondingly their efficiency is higher when compared with polycrystalline. They should be mounted on a rigid frame, okay, for the protection. Next is polycrystalline or multicrystalline cell. So they consist of several small crystals. Monocrystalline was having single crystal. Now polycrystalline, they are having several crystals called crystallite. Then the raw silicon is melted and kept in square mold. Then it is cooled and sliced to make square wafers. So here in the diagram, they look like square wafers. Polycrystalline solar panels are of rectangular shape without having any round edges. So in monocrystalline, there were round edges, but in polycrystalline, there are not any round edges. So these cells are less efficient. Yes, comparatively, the efficiency of polycrystalline solar cell is less as compared with monocrystalline cell. But they have an advantage that their price is less. Means monocrystalline is having a higher efficiency, but they are having a higher efficiency, but they are having higher price, whereas polycrystalline are having lower efficiency, but the price is also less. Both of them, they need to be mounted on a rigid frame. Last one, the amorphous cell. They are formed by placing a thin film of non-crystalline or amorphous silicon onto a wide range of surface. They are flexible. Their efficiency, that is low, with their cost, that is very less. The output power of amorphous cell that reduces over time, especially during the first few months. That means earlier the efficiency is high, but then suddenly it will go very fast. It will be reduced. It will come down. After that, it will be stable. Okay, so after the efficiency gets stable, that stable efficiency that is considered at its normal efficiency. So initial duration, the efficiency is high. That we don't consider as its normal efficiency. Efficiency will be considered when after the reduction in the efficiency is taken place and a stable range is given. Okay, so some of the questions here, similar formula based. Then I shall stop here.